So welcome everybody again to this seminar series of Talent Q and Quantum Spain. So this is a great pleasure to have today Davide Rusca with us. And so you will notice that we decided to open our scope, and this talk will be slightly off the mainstream that we have been following during the last months, mainly algorithmics and quantum computing. So I think it's we decided to open the window and let some fresh air come into the room and learn other things that are certainly related. But and I also asked Davide to be to explain things from a little bit from scratch, so that we will really want to learn. So at the end he might go more complicated. So let me introduce Davide. Davide is here in Galicia, where I'm now. And Davide received his Master of Science in Physics Engineering in Milano, in the Politecnico, in 2016. So with a thesis focused on the design and fabrication of photonic chips on glass. Later, he went to the group of Hugo Swinden in the University of Geneva, where he made his PhD, and his work focused on the security of QKD, quantum key distribution, and on the implementation of quantum random number generators. He received the PhD in 2021, after which he spent a couple of years in the same group in Geneva. But then in 2023, he came to Galicia and he joined the Vigo Quantum Communication Center as a senior researcher in quantum communication technology. Okay, so the title of his seminar today will be Quantum Randomness from Theory to Experiment. Davide, we are really thrilled. The stage is yours.
Thank you very much for the kind introduction and for the opportunity to participate in this seminar. So, hello everyone. As Javier kindly said before, I'm going to talk to you today about something a little bit different than quantum computing. I'm coming from the world of quantum communication and related quantum technologies. So today we're going to explore a little bit the ideas around quantum randomness, and I hope that we will also explore a little bit the ideas of randomness in general. In fact, I would like to start from there, because it's true that for all of us, for pretty much every human, it's very natural to think about randomness. Now, when we think about something random, we think of an event which occurs with unexpected probability. So, like, this can be represented most of the time with something practical, like the throw of a die or the toss of a coin. But it's when we try to investigate a little bit more deeply what is randomness that I think things start to get a little bit more complicated. For example, in this scenario with some physical devices like this, it's easily understandable that we can be tricked, no? Like the die can be not perfectly random. We can maybe foreseen the event of a coin toss if we are very skilled in launching it. And so now we have to understand what is randomness, but how can we do it? Can we maybe assert it from the occurrences of it? No? For example, if the coin toss that we have, we assign a 0 or a 1, by looking at the number that appears, can we say something about the randomness of the coin? But it turns out that for a certain number, like for a string of a certain number of bits, every string should be equally possible. So even something that for the human eye, maybe, or even for a computer, could look completely non-random, in reality should have the same probability as any honest string to appear. So it becomes a little bit more complex to understand what actually is randomness. And first of all, we should also ask ourselves what properties should something that is perfectly random have. Now, for example, is saying that something is uniform, no? That from a set of events, like each event is equally likely than every other event. Is this enough? For example, if we have a string as before of n bits, no? If each string has a probability 2 to the minus n, would this be enough? This maybe would be enough for some application, for example, in gambling or in Monte Carlo simulation or in simulation in general, where the uniformity of our numbers is enough to reproduce the results that we need. But for one application, this is for sure not enough. And this is like the main aspect of my research, which is quantum secure communication, which is cryptography. So in cryptography, we don't only want to generate a string of bits which is uniform, no? So, but something that no one else can foresee. And this is not true only for quantum key distribution, but any cryptographic scheme which requires the generation of a random seed or a random key. Why is this not enough? Because if someone else has an exact copy of our numbers, even if our numbers are completely uniform, so maybe they're produced from the ideal random number generator, but if someone else has them, then this person can foresee each and every one of the numbers that we are going to produce. So it's not only needed for our randomness to be uniform, but also to be private, no? For application which requires security. No? And in this case, how can we make it? No? So then here, this private condition makes it such that now the production of random numbers becomes somewhat a little bit more difficult. In fact, I think that for every one of us that have programmed something on a computer and used a random function, we are used to what is algorithmic random number generator or pseudo random number generator, where we inject a seed inside a machine, and this machine, by a complex algorithm, outputs a longer string of numbers, which has a period of a periodicity which is much longer than the seed that we are using. And this, it's used, and many times is even sufficient. It's used to generate something that looks random, with the pattern. There's not enough patterns inside the sequence such that it could be foreseen at one of the next numbers, but of course, this has a drawback, which is that if someone comes in possession of the seed that were used for our algorithmic function, then it could foresee all the numbers that we're going to produce with our algorithm. So this is good or enough if we want to make some simulation sometimes, but for sure it's not enough if we want our numbers to be secure. So another way into tackling this problem is to access instead physics. So to try to convey, to explore what is information inside of physics. And then one of the first approach that was used even before, let's say, relying on quantum mechanics was to try to exploit what we see, the noise in the equipment that we have in the lab. No, for example, for the experimentalist in the audience, no, we know that we have some noise related to any possible measurement, no, electronic noise that we have, and this noise looks to us completely random. What we do is that if we can harness then this noise, we can take this as a source of entropy, amplified, discriminated with a comparator, and we pass from an analog noise signal to our nice digital random string. Of course, now, like, there's a lot of different approaches that go under this what is called in the literature true random number generator, physically true random number generators, but there's a little bit of a problem inside of this approach. First of all, if you want to have a deeper dive inside all the classes of, let's say, classical random number generator, there's this nice white paper from BSI, the German institute, that gives a nice overview over all the classification of possible random number generator. But of course, here, like, if we were satisfied by this explanation, or we could stop the talk. But of course, this is not enough, because the problem is that if we want to see randomness just at the output of our device, then this would be enough. But as I said before, it's impossible to understand if a sequence of bits is completely random just by looking at it. Not just by the occurrence of it, we have to model what's before. And of course, how do we model what's producing this sequence of bits is the importance in random number generators. And unfortunately, if we use classical mechanics, this is not enough. Now, we can think of a chaotic system, not that it's not robust with respect to the initial conditions, such that if we have slightly different initial condition, we end up in completely different results. But it's true also that if we know perfectly well the initial condition of our system, even if it's chaotic, by modeling, we should be able to understand what is its outcome. Of course, here for the people among you that are already knowledgeable about quantum mechanics, they could say, okay, but it's impossible to know the initial condition perfectly. But this is exactly the point. We have to access a new theory in order for us to explain randomness. So it's nice because something that it's completely intuitive for pretty much everyone, we understand that it's not explainable by the by a simpler theory than quantum mechanics. And then it's very nice to see that quantum mechanics, it's what takes and makes randomness, this simple concept, completely possible. Why? Because I think that every one of you already knows, but just for clarity, we can restate, because it's an intrinsically probabilistic theory. So we have some state preparation and measurement, which are not compatible one with the other, and the result of which will be different, even if we prepare in the state always in the same way, and if we prepare the measurement always in the same way. Okay, so this is a peculiarity of quantum mechanics that in this specific case we can use exactly at face value to generate randomness. And this is not, of course, something completely new. No, this is something that was already done back in the days. And we're going to see now, we're going to take a small dive inside the history of quantum random number generators, from the early, let's say, development to the more recent ones, which I was also able to work with. So first of all, I would like to take a small step back, saying that when we talk about a physical random number generator, but in our case a quantum one, we always separate it in two parts. One, which is our entropy source, so the physical device that actually generates our raw string of bits, and then a post-processing. Because of course, if let's say we have a bias, so we know that we have some noise that we have to take away, we can do this by post-processing it, and we can distill in this way a perfect random number generator. This is something I want to say here. Of course, I don't have time to go into the details, but when we talk about this, just to be clear, when we talk about this quantum random number generator, but in general, for many physical random number generators, there's always a part of physical entropy source and always a part of post-processing done after. Okay? In our entropy source, of course, usually we have a source and a measurement. Okay, of any sort, and we're gonna see a few examples of these schemes. Of course, how do we value the randomness now of what we generate in between these two parts? We have different ways. No, like for example, we can use Shannon entropy, no, which gives us the average information that we have at each round, given our probability. That it's describing our phenomena, but usually for quantum random number generator, it's another quantity that it's used, which is much easily much more easily describable in an adversary environment, which is the mean entropy. The mean entropy is related to the most likely event in our probability distribution. Okay, by this simple formula. And the nice property of the mean entropy is that 2 to the minus its value gives us the probability that anyone has to guess the output of our device. Okay, so you see why this is a nice quantity to interact with, because if we can model this probability of guessing, what we are doing is that we are essentially asking ourselves how likely it is that anyone, okay, not only anyone that has access to the laws of physics and it's limited by the assumption of our device, can guess our output. So this is a quantity that if you will read about quantum random number generator, you will come into contact quite a lot. Okay, so now let's dive in some. There's a hand raised. We can.
Hey, Andres, I think that you can speak now.
Has to mute. It's muted.
No, he's not muted.
Okay.
Sorry, but it was an accident.
Okay. No, but it's not. Okay. So no, but it's good because it's a small pause before we dive right into the examples of quantum random number generators. So the first quantum random number generator that was developed back actually in the 50s was related to isotope decay. Okay, so we know that there was a lot of research in atom physics and isotope physics back in the days, and they realized that this decay, of course, this was already known quite rapidly by the community, but to harness this for randomness generation was actually quite like the first step into this technology. And it's nice because like one of the first example of this was done with strontium 90, which decay with beta decay. And this decay has an emission which is easily detectable by a Geiger tube. And if we harness the time of event in which this decay happens, we can create our random number generator. One way to do it practically is that if we have a clock, for example, if we have a fast clock, faster than the average click rate of our Geiger tube, what we can do is that we can XOR each event with the clock that we have. And if we have an event, we can output the bit 1. And if we have no event, we can output the bit 0, for example. And of course, this decay is completely probabilistic, and it's modeled by this formula here, which gives us the probability of a decay inside an infinitesimal time domain. And then we see that here we have the spirit of our quantum random number generator already in this prototypical formula, which is our source of entropy, where we have a source and a measurement. Then we generate a raw stream of bits, which we can further post-process with our extractor, etc. Okay, of course, this was the first attempt, and it has like some pros to it, which is that we get some actual quality random number generators. So we don't have any problem of getting ourselves correlated with some unwanted noise. Now we can characterize it, but the process in principle, it's completely random, given to us by quantum mechanics. Unfortunately, this is not very practical. The accessibility of material that can decay in this way, are not very safe, are not very practical to use. We need to shield ourselves, and it could be expensive, etc. They're not small, and moreover, they're not even that fast. So, they weren't very practical nor performant. So this wasn't the way to go, even if there was quite a lot of research that went into this, and even today they're still used here and there. But then there was a huge change in quantum random number generators in the early 2000s. We had we had access to a very mature technology, which was optical quantum optics and photonics, and many people access this trying to harness their property. For example, if you remember before, I showed you the formula of the superposition of a state between the eigenstate 0 and 1, no, and its projection in its non in the other basis, no, like we had a state in the x basis and we were measuring it as z basis. How can we do this with light? And this, it's actually very comfortable in theory, because we can encode the information of a qubit in a single photon. We can use different degrees of freedom, and it has been done in many different ways. For example, it has been done in polarization, it has been done in path, in time. We can see a few examples here. Here, I present to you one of the simplest one to understand, which is polarization. What we can do is that we can encode our photon in the diagonal polarization. So a superposition of the horizontal and vertical polarization. By letting it pass through a polarizing beam splitter, which separates the two components of horizontal and vertical towards two single photon detector, what we can do is that we can assign the value of 0 and 1 respectively to the two detector, and these two detector will click one or the other, because we have only one excitation, one photon, and the probability of this detector to click is going to be exactly 1/2 if the states and the measurement that we have made are accordingly to our blueprint. Of course, this it's easier said than done, no? Like, as we will see later. But there has been many attempts. For example, like this, there's few examples in the year 2000. One that I'm a little bit fond of because it's originally from Geneva is done with a LED light. And like this LED light was attenuated enough such that we have almost zero probability to have two photons at the same time. A pulsar would pulse this LED light, and then we would stream it inside first a single mode fiber and then two multi-mode fibers, where one of the two fibers had a 60 nanosecond delay with respect to the first. And then you see that we have these two pulses that are going into two different paths, and one of these paths gets delayed with respect to the other. And then we see that before it was in polarization. Here, what we have is a superposition in time. Okay, so what happens is that now either the photon is going to be detected early or late inside our chain of triggers that we can see. And then we can harness if we get early detection at the bit 0, for example, and if we get a late detection, we can have bit 1, for example. And then, like, this was very, very nice because this device starts to be a little bit more compatible with the application. Here we don't have any radioactive material. We have actually some components which are pretty easy. Like maybe the most complicated component in this chain was this single photon detector, which in the year 2000 was still like a little bit of a novel technology, but that nowadays we know we managed to miniaturize quite a lot. And then from here, like the world of like the state of the art started to try to improve both in practicality of the experiment, but also in performance. Okay, and then we see, for example, two works which I think are quite nice. One always from Geneva. Of course, I have to say the works that I'm presenting here are not the complete overview of all the literature that is around, and I am, of course, bringing a little bit of the experience that I have before in Switzerland and now here in Spain. Because the second experiment that I wanted to show, it's exactly another one done in Geneva, and it was in 2014, and this is very nice because also the other work that I'm going to show you is in 2014, and they have a similar outcome, not in the experiment but in what happened after. And in this case, instead of using the LED as a single photon source, so like trying to mimic the work of a dim Poissonian distributed light to a single photon source, here the idea was to exploit exactly the Poissonian distribution, the Poissonian nature of the photon, the number of photons emitted by a source like an LED or a laser. And the nice thing was that in this case, what it was used was not a single photon detector, but a CMOS. No, so it was actually in this experiment the camera of a cell phone. No, so we see that we went just from from using radioactive material to something that we have in everyday life with us at all times, more or less. And here the idea is that if the number of photons emitted by our LED light have this Poissonian distribution, this has a certain randomness in the number of photons that we are going to generate. And then if we translate this number of photons, of course, it gets translated by our detector into an analog signal. This analog signal we can amplify and then translate to or convert to a digital sequence. And then we can estimate the amount of noise that it's due, for example, to all the electronics that we have inside our circuit, and subtract it and remain just with the Poissonian nature of the noise given by the distribution of number of photons of our LED. Okay, and this was a very nice experiment, which puts us put the number the technology of quantum random number generator more towards the applicability of this technology, not only in the, let's say, proof of principle. The other example that I wanted to give is instead was done in ICFO, always in 2014. And in this case, the source of randomness that was used was the phase of a gain switched laser. So if we gain switch a semiconductor laser, for example, the phase of each pulse that we generate is going to be random with respect to the previous one. Why? Because the spontaneous emitted photon, which generates the avalanche of photons inside our cavity, makes it such that we have no coherence between two following pulses. And this we can exploit by making an unbalanced interferometer. In this case, it's a Mach-Zehnder, where we have our train of pulses going in one arm and in the other, and gets delayed by exactly the repetition rate of our, the distance between two following pulses. We do this because then each of these pulses that gets to interfere after, at the end of our interferometer, will generate a random level of intensity in our pulses. Of course, this distribution of intensity is not going to be perfectly uniform. We have to make some adjustment in order to get a completely uniform distribution after, but nevertheless, we get this randomness and we translate it from the phase of our pulses to the intensity of their interference. Then we get a linear detector and an ADC as before, which converts us our analog signal to our digital sequence. And why did I choose these two examples? Because actually it's quite nice to see that they were then implemented in the two companies. So the first example was used by the Quantique, which was founded a little bit before. So it's not the product that made this as a spin-off, but instead QSide was actually made out of the idea of a quantum random number generator company. And the idea for both companies now it's to go towards miniaturization, low power consumption, and high rates. Now both of them are now in a very, very small form factor, could be used. I think ID Quantique 1 it's also present in a phone. And of course, this is not to make advertisement to this company. I think you are not the audience that will actually buy from any of them. But it's nice to see that something that goes all the way from just a proof of principle, very far-fetched, and then becomes more and more applicable and becomes something that we can use in everyday life. No? So, and this is nice because for many technologies before this was a given, but for quantum technologies, this for sure, it's something that we would like to see for quantum random numbers, for quantum key distribution, and for quantum computing. Of course, there's a problem. There's a conceptual problem in all these devices. No, we are we always said, like, for example, I have a single photon source, but then I showed you an LED, like we have a laser source, but then there is a lot of components inside. So every device that I explained before, that I presented to you before, it's what we call device-dependent quantum random number generation. What does it mean? That we have to characterize each component of our device in order to rule out any possible source of classical noise. Now, for example, in the case of having a single photon, a beam splitter, and two detectors, what if we have an LED instead of a single photon? What if we have two faulty or like with a limited efficiency single photon detectors, which also can have some noise? We have to rule out all the classical noise in order to extract our quantum randomness. Of course, here I call classical noise anything that it's not modeled by our quantum model, but it could be anything, of course. So in the research, there has been a lot of effort to go in this direction. And one example of this was the so-called device-independent approach. So the idea is, okay, what if we have a completely black box? Okay, this is also like, this is a completely black box with some assumption, let's say, but for sake of the story that we're taking, let's say that we almost make no assumption on what we have inside the devices that we have here. And then what we do is that we probe the device with two separate inputs. And one of the assumptions that we have to make is that these two devices are actually space-like separated. So the input X cannot influence what happens to the second box, and the input Y cannot to influence what happens in the first box. And then what we can do is that by non-locality, okay, we can infer the result of our measurement to be completely random. Okay, so this actually takes, of course, inspiration to, and it is a Bell test, a Bell inequality experiment. Only that in the, let's say, original Bell inequality violation experiment, what we were trying to consolidate, to corroborate, is the validity of quantum mechanics. But here we take another step. Here what we do is that we assume quantum mechanics to be true, okay, and we use the consequence of this test to generate randomness. Okay, so in the case of like a Bell test, what you have to do is that you need an entangled source in the middle. You have to send it to our two measurement, and the two measurement have to be switched by an input X or Y, depending on which box you are in. And if you manage to violate, in this case is CHSH, but if it's another Bell inequality, it can work the same. You can prove that your device is not working classically, so you cannot infer the outputs that you have because the states and the measurement that you are making are completely fixed. So if you reach the limit of quantum mechanics, you can prove that the state and measurement are actually specific ones. And of course, if you are in between the classical bound and the quantum bound, you can still prove that there is some quantum randomness here. Of course, I'm not going to explain exactly in details how this works, but I just want to give you an example of what happens, like how do you actually make it. And now you see already a drawback of this, because you could be a little bit driven to think that like this is the perfect solution, but the problem is the complexity that relies behind all this machinery. First of all, we have to generate an entangled state, okay, which is not completely, like, it's not trivial. Now we have to, like in this case, they used a laser diode, an amplifier, a PPLN crystal, and then a Sagnac loop in order to generate our pair of entangled photons. One photon has to be sent on one measurement basis and the other to the other, and we see already a small details that maybe could make someone already question the whole experiment, which is we need two quantum random number generator inside our experiment. Because of course, what happens is that the inputs of our device has to be unforeseeable by the other box. And the only way to enforce This is by generating, of course, the bits randomly. And this could seem as a short circuit, no? But there's many reasons behind it why this could still work. First of all, it has been proven that you can expand actually the randomness that you need with respect to the one that you produce. Okay, so eventually you can feed what you generate inside your own device in order to generate an infinite amount of random numbers. But also, even in the context of having two device-dependent, let's say, QRNGs inside your setup, what you're doing is that you're making your setup more and more reliable, because, of course, now the failure, like maybe the two random numbers that you have are not completely perfect. You need to characterize them, but then by making all this machinery, you generate something that it's more pure, no? Something that doesn't require you to characterize the whole thing. Okay, but of course now I was of course in explaining you the pros of this technique, but of course the cons are the practicality of this experiment, which is not very high, of course, because we need a lot of components. We need to violate Bell inequality, which for you that maybe read something about it, it's something very complex, not something that cannot be made compact, not yet at least, and the rates are very low. No, like actually it looks a little bit like the radioactive decay quantum random number generator. So now we showed two main approaches to quantum random numbers. No, one which is fully device dependent, let's say, where we have to characterize everything, and another one which is fully device independent, which, let's say, requires the minimum amount of assumption that you need for this to be proven to be quantum. And this is something that I always like to do, is to put them in this imaginary graph, where on one axis we have the performance that we can evaluate with the bit rate of our device, and the device independence, no? or the level of paranoia that we have regarding our quantum random numbers generator. Of course, the ideal would be to have something which is completely device independent and have a very high performance. But this, of course, it's almost unachievable. So the idea that was done in the latest part of the 2010s was to have instead a semi-device independent approach. So let's make some more assumption than a fully device independent scenario, but let's try to have comparable rates with a fully device dependent approach. And now I'm going to explain to you a little bit this kind of approach, which was also the one that I worked the most with. Okay, so first of all, why do we need to be paranoid? No, like you may ask yourself, like, what is all this need of trying to make your device device independent and everything to be like I'm not fooled by my device not to be perfectly random, but sometimes you can fool yourself in making something that looks random, but it's not. Okay, and maybe your model it's not good enough. And here is what it shows. No, like normally your device, no, like that could be this one, but any other, it's modeled by having a state, no, and a measurement which has two possible outcome. No, in this case, modeled by these two POVM elements. Now, if everything works fine, no, the probability to have 0 is given by the Born rule. No, like we can write it as the trace of the product of our density matrix with our POVM element. And if we make everything correctly, no, we would like to have here 1/2 and 1/2. No, so this is perfect. But what if actually an adversary tampers with your measurement device? No, so what if an adversary has a set of hidden variables inside your device, and now what happens is that once you send the state, you still get 0 and 1, but this time, if the adversary chooses lambda to be equal to 0, you get a POVM which always outputs 0, and if the adversary gets to choose a lambda variable equal to 1, then you always get something, like you always get the result 1. And then you may ask yourself, okay, but then I should be able to see this. But what happens is that if now you see the compound result that you get if chooses the probability of lambda equal to 0 and lambda equal to 1 equal to 1/2, you will see something that is completely random at the output, but it's perfectly correlated to the adversary. So the adversary will know perfectly the result that you have just by looking at this lambda value here. Okay, so this is a little bit what the adversary will try to do, is to have a lookup table. So the adversary doesn't have to be inside your box, no? You can have just the list of all the sequence of this lambda value that are going to be used inside your box and output that. And then she will know exactly what you have inside your device. Okay, so this is a little bit the adversarial scenario that we would like to fight in our semi-device independent approach. And how do we make it? No, so exactly like this, we would like to have a device which we can divide in a source and a measurement. But now we don't only produce one state, but we can switch between two given an input to our source. We would like to make just one small assumption to the source that we have and almost no assumption to the measurement device that we do. Exactly for the reason before, no? Because someone could tamper with this and could make it easily output what something that is correlated with them and looks random to us. So what is the assumption that we take? The assumption that we take is that the states that we generate have actually a certain overlap, which is not zero. What does this mean? That our states are not orthogonal to each other. And quantum mechanics tell us that actually, if two states have a certain overlap, so are not orthogonal, we cannot distinguish them perfectly. Okay? So we cannot have a scenario in which I produce states with this overlap and with 100% probability, I can distinguish them with my measurement. There's no measurement that can do this. Okay? And this is a property of quantum mechanics that we would like to infer. And why is this important to us? Because what happens is that now, if we look at the input-output probability that we have, we can infer the probability that someone has to guess our key. And to give you an idea to why this works, we can think it like this. If we have our setup, no, where we give our input X to our source, and we generate one of the two states, psi 0, psi 1, then the adversary that has the control of the measurement box has two possible choices. Now, either they make a perfect measurement, and then they try to mask the noise with the lookup table as we've seen before. But the problem is that let's say that our input-output probability match exactly the best measurement strategy that quantum mechanics allows. Then Eve cannot feed any of their bits inside our sequence because it's forced to use the perfect measurement. Otherwise, this would not match the perfect scenario. Okay, so this is a little bit the idea behind this semi-device independent approach. Okay, so now I would like to give you a few examples on how this works. Maybe I can pass directly to the important one that it's the a little bit more technical part of the talk, where I explain actually how this works more in detail. So we said we want to generate two states with a certain overlap. What we do is that we generate two coherent states and we modulate them between the phase 0 and pi. Also, if we look them in the phase space, we see that if alpha is small enough, these two states will have a certain overlap. Okay, so will not be perfectly distinguishable. This is easily you can easily picture it with an image in the phase space. Now, what we have to do is that we actually have to make a measurement which is close enough to the ideal measurement as we can. Of course, we cannot make an Elstrom bounded measurement, but we can go close. And the idea to do that is to make a homodyne detection. So what we do is that we project these states in one quadrature, okay, and then we try to distinguish it. And this is the homodyne detection. No? So what happens is that you make your coherent state interfere with a local oscillator, and then you distinguish them with two balanced detectors. And then what you do is that if the signal is positive, then you assign a bit 0. If the signal is negative, you assign a bit 1. And then you see that these two bits are correlated with the states that you generate, because it's more probable to get a signal, for example, 0 if we send alpha than if we send minus alpha. Okay? So how do we actually make it in the lab? No, and now this is a little bit more on of the trick, no, because it's nice until like we see that we have our concept model, no, the gray and black box. Then we have our blueprint of the setup that we have to do, which was the previous slide. But now we actually have to make it in the lab, and this is not trivial, not to actually make it properly. And now you see, though, the advantage of this approach, because here what we do is that we have our laser source, which is in continuous wave and 1550. We inject this laser source inside an interferometer, where we have on one arm our prepare box. Now, so here what we do is that we get the coherent state, we modulate in phase, and what we do is that we monitor its energy, which it's going to be related to the overlap of our states, and then we attenuate it as much as we need for our protocol to work. And the nice thing is that all that we actually have to characterize is only in this box. The rest, which is what we can assume, what we can infer to be the measurement, does not have to be characterized. And what is this? It's just the other arm where we get our piezo in order to match in phase the local oscillator and the signal, and then the interference between the two, but most of all, the homodyne detection itself. And this is important to have inside the uncharacterized part, because every source of fast noise, which would be difficult to characterize, is actually not needed, okay? Because it's already taken into account in our scheme. So now if we measure the input that we get by modulating our phase and the output that we get by our discriminator after the homodyne detection, in this case was managed with a film programmable gate array, we can, in this way, generate our random numbers. Okay, we can estimate what is the mean entropy and extract it with the post-processing in order to obtain a perfect random number string. Okay, so here, just as I said before, no, this was the only part that actually needs to be characterized, no, which is the attenuator, the mean splitter, and the linear detector that we have here. In this experiment, we were modulating at 1.25 gigahertz, which gave us, in the end, at the optimal level for the mean photon number, almost 225 megahertz of true random number generation rate, which is already quite good. No, it's not as good as the device-dependent approaches, but it's high enough comparable to them. No, so of course, and this is a much newer technology. Okay, so finally, this was the measurement that was done in time in order to see, and now you see another property of this experiment. No, this is the rate in real time. No, so it was taken different measurement, and now another property of these self-testing or semi-self-testing devices is that we have an estimate of the entropy in real time. So meaning that if something goes wrong inside of our device, we immediately understand it. Okay, so if something breaks inside the measurement that we have, that we didn't characterize, we will not produce enough randomness, and the estimation that we get from the conditional input-output probability will give us this red flag. Okay, so with this, I would like to conclude my talk. I think I also almost ran out of time. And first, like before leaving you, I would like to give you few more papers. Like these are nice reviews that collects the history of quantum random number generator. A few of them are a little bit older. Some like one is a little bit newer that should consider also the newer stuff came out in the last years. But with this, I would like to just give a small shout out to the group here in Vigo that is now almost 2 years old, and we're doing some new work. And with this, I thank you all for the attention, and I'm happy to answer if any question arise. Thank you very much.
Thanks, Davide. That was a pleasure to hear you. So if anybody has a question, please click on the raise hand button, and we will unmute you. So Javier will unmute you for any question. Yeah, no questions. Everything is pretty clear. So maybe I just ask. I mean, a very very simple thing. So I'm a little bit ignorant of this, but if I see a sequence of random numbers,
Yes.
to a certain the randomness, it's enough to compute the entropy.
So the thing is that in principle, like to this answer to this question, there's a few tests that try to see the quality of the source. No, but like intrinsically, like, it's impossible to tell. No, because if you have a sequence of numbers, no, like each random number generator should be able, like each perfect random number generator should be able to output it. Of course, it's like there are some sequences which are very unlikely. No, so like what happens is that you have this test, which even an ideal random number generator would fail with a certain probability. But the problem is that in a context of security, let's say that even if you have a sequence of random numbers, which is perfectly random, no, it was generated by a true random number generator, like an ideal one, you need not only to be sure that this sequence of number was like it's perfectly random, but also that no one else knows it. So you have to make something that produce it, and you're sure that it was produced by that device and not by something else, and now it's just feeding you the existing randomness.
Yeah, but imagine, I mean, your problem is a different one. You want to do a Monte Carlo, for example.
Yeah, no, but
in order to be sure that you're using really a truly random thing, what test would you do on the generator?
So there's these die-hard tests, which have like these statistical tests. Of course, this to all means and purposes, I think it's enough to test if your source is good enough. But this is also, like, to me, at least, like, I see the application with a kind eye. I'm happy to see all this getting a commercial like a commercial avenue. But for me, it's more somewhat more of an like fundamental problem, to understand what is actually random. So for me, it's not enough this die-hard test to prove that something is completely random.
For you, it would be also to add the privacy.
Yes, exactly. Exactly. The thing is that, yeah, and then you should be sure, and to be sure that something is random, you cannot just look at the output, but you have also to know how the source works.
I think there was a question there.
Yeah, thank you, Davide. It was great. I was very happy to see you mentioning quantum randomness from CMOS sensors, because we are collaborating in a project in that regard, using the light that enters the CMOS sensors of smartphones or whatever camera. And I just wanted to ask how to get in touch with you to follow up on this very precise content.
I didn't, you're right, I didn't put my contacts in there, but if you go on the VQCC website, you should find my email in the team section. So this is Vigo Quantum Communication Center, and there should be my email address.
Thank you.
I think I could also share it. If I put it in the chat, like I share it for everyone.
Yeah.
Okay, then I put it in the chat. So
thank you.
You're welcome.
Yes, that was an easy question to answer.
Yes.
Yeah. Good. So, well, I think this
There is a question on the.
I didn't see it. Yeah.
No. Sorry.
Okay. Then I think this was all. I think I want to thank Davide for his gentle seminar, and we convey you for the next seminar in this series in 2 weeks. So stay tuned, and see you again, everybody. Yep. Goodbye.
Thank you.
Yes.
Bye-bye.